Hello, my name is Daniel, and this is my project on neuronal firing on a fractal. Over the last 10 weeks, I've been striving to learn more about the effects of a biological neuron model, known as the quadratic integrated fire model, shown on the left-hand side of the screen. This is a slightly more complicated version, as we'll see down the road. And we apply it on a unique topological structure known as the Sierpinski gasket, which is shown on the right-hand side of the screen, where each triangle of the gasket is equivalent in geometry to a smaller triangle within the gasket. And so applying this equation to the gasket may prove to show very interesting patterns as a result of its self-similar properties. So in order to programmatically apply this equation to the fractal, I first had to create an algorithm that could generate an adjacency matrix for any approximation of the gasket. An adjacency matrix would allow me to know all of the neighboring nodes for all nodes on the fractal, and would allow me to apply this equation to the gasket across all of the nodes' trajectories. A basic understanding of how this algorithm would work is that you would first have to create a 2 by n matrix where each column representing a node has two unique addresses, and then applying this matrix to generate an adjacency matrix for the gasket. In order to build this matrix, I developed a match function that deciphers whether two addresses are equivalent. This requires the first few digits to be stripped off until they can be compared for equivalency. After I developed this algorithm, I applied the coupled stochastic version of the quadratic integrated fire model to the gasket. Compared to the ordinary quadratic integrated fire model, this has a coupling factor with a graph Laplacian term with a stochastic white noise term. And because of these two terms, it affects the random perturbations that you get in the curve, as well as the number of spikes that you get in the curve, as we'll see. So after applying this equation to the nodes of the fractal, I found that after numerous numerical trials, increasing the value of k, the coupling factor in the second term, decreases the overall firing rate among nodes on the gasket, as well as makes clusters in a cluster plot of the firing decreases it decreases the clusters to a smaller subset of nodes, as we'll see in the next slide. And so on the left-hand side, we have a graph of the firing rate versus the coupling strength. And so this just shows as you increase the coupling strength, the overall firing rate among all nodes on the gasket declines. And similarly, on the right-hand side, this is for a relatively small value of the coupling factor. As you increase the coupling factor, you inadvertently decrease the overall firing across all nodes on the fractal. And so some conclusions that we can make off of these results is that there does not seem to be any form of global synchrony across the entire fractal, meaning that all of the nodes aren't firing at the same time. We don't see lines of dots that are showing that all nodes are firing at very similar, or if not exact, at the exact time step. However, there does seem to be many cases, as we'll see on the left-hand side, these small clusters of nodes where they're firing among very adjacent neighboring nodes in very similar time steps. This seems to reinforce the fact that every node on the gasket has four neighboring nodes, and thus coupling would be stronger among these more adjacent nodes than nodes further away on the fractal. Another example of this are the results one would get from applying equation 2.2 in Dr. Medvedev's paper, the synchronization of coupled chaotic maps, shown on the left-hand side of the screen. Here I've also found, after applying this to the gasket, I found that there were these smaller subsets or pockets of nodes of adjacent nodes that were showing synchrony across the entire fractal. And so these very close pockets of nodes were much more coupled than the entire fractal itself.